Dr. Zaius, Dr. Zaius, Dr. Zaius, Dr. Zaius, Dr. Zaius, Dr. Zaius. Oh, Dr. Zaius. Dr. Zaius. So this is the electric potential problem, the voltage example, number 8. It's our last example we're doing. And in it, we have a 35 microcoulomb point charge, and it is 32 centimeters, so next to an identical charge. So it's another 35 microcoulomb charge. How much work is done to move a positive 0.5 microcoulomb charge, which is initially midway? So let's draw it in the middle here. So here is our 0.5 microcoulomb point charge. It's midway, 16 centimeters from the left, to a point 12 centimeters to the left. So we move it 12 centimeters this way, and it shows up 4 centimeters away. So this is our initial position, and this is our final position. Okay? Well, how do we go about doing this? Well, if we want to figure out the amount of work that is done, it is important to remember that we think about work as being a charge moving through a potential. That would be like an electrical potential energy at this point. This is the potential V, the voltage that exists in some space, and Q is that intrinsic property, that charge that is being moved through it. And if we want to think about it like, yeah, there's a negative that goes in there and whatnot due to the idea of infinity is 0 and blah, blah, blah. But let's just ignore it for right now because we're just seeing how much work will be done. Okay, I don't care about what's doing the work. We're just considering, is that work being done? So we know this work equation, work equals Q times V, the charge through the potential. Okay? Now, we know what that charge Q is. That charge Q is the 0.5 microcoulombs. So that's straightforward. That's 0.5 times 10 to the minus 6. The real question is, what is this V? Well, sidebar. Remember, this voltage we have here, that isn't one number. A voltage is a potential difference. That's actually a difference between two voltages. Normally, we consider a point an infinite distance away as being the initial voltage here, the voltage that we reference to 0. So if this is a final voltage minus an initial voltage, we normally consider this as being 0. So we just say the voltage. It's just V. But that doesn't need to be the case. And what we have here, we have 2 points, one from the center and one over here on the left-hand side, that will both have some numerical quantity for the voltage there. And we need to find that voltage difference. So what we're going to have to do is to find our voltage in this problem, we are going to have to take the final voltage minus the initial voltage. And what we need to remember here is that for each of these voltages, the final and the initial, this is made up of not one, but 2 point charges and their positions in space, okay? So we need to take both of these point charges to add them together in order to get this, but these are the final positions, and these are the initial positions for those voltages. And that summed together will give us our actual voltage, which we'll plug back in to the equation here. So it's not bad to do, but there's a little bit more math that goes into this one compared to problem 7. So let's get boogieing. Let's start by getting the initial positions, or the initial voltage here. Remember, this initial voltage is the combination of both charges, 1, where it is initially, and 2, where it is initially. Now, a nice thing for us is that since these charges are identical, and they're an identical distance away, both are 16 centimeters away here, if we just do this once, we can multiply it by 2, because they're the exact same, and we get our answer for the initial voltage here. So we'll do this by saying it's twice, because we've got 2 of the exact same thing, okay, times KQ over R. So there's K, here's Q, there's R. And in this case, it's going to be 2 times 9 times 10 to the 9th times the charge here, which is 35 microcoulombs, so 35 times 10 to the minus 6, and then divided by 16 centimeters. And to put that in meters, that's 0.16 meters right there. You throw all that together, and you're going to get a pretty large number here. We're going to get 1968750 volts, and then actually it's 2 times that quantity. So it's this times 2. This is what it is just for the KQ over R, and then we multiply that by 2 because we've got 2 charges, and we get the total initial voltage here is going to be double that, which is 3937500 volts. That's our initial voltage here, okay? Now, let's figure out what the final voltage is. To do this, similar procedure, our final voltage is going to be equal to the first charge's final, with the final distance, plus the second charge, which is final distance here. This is slightly annoying because these have different radial positions. For the first one, we're only 4 centimeters away. But for the second one, oh man, what is this? This is 12 plus 16, right? It's that huge distance right here. So that gives us 28 centimeters, a much, much longer distance in comparison. So to do this, what we're going to have is, for the first charge, we're going to have the kq over r, which k is going to be the 9 times 10 to the 9th. The q is going to be the 35 times 10 to the minus 6. Those are our microcoulombs. And then divided by 4 centimeters, so 0.04. Plus the second voltage, which is going to be kq over r, but with a different r. So 9 times 10 to the minus 9 for k. The q is still the 35 times 10 to the minus 6, because the other charge is identical to the first. And then this time it's divided by 0.28. Okay? This will give us the final voltage at that position in space. So this is a little bit of math to work through, but when you do it, you find out this final voltage here is going to equal for you 9000000 volts. It's a huge number. Okay. If you got something different, check your math. I may have done a little bit of rounding there. Okay. At this point in time, we have our final voltage and our initial voltage. We have that. Boom. There's the initial. There's the final. So to get the actual voltage in this problem, and remember, this voltage is the change in voltage, what we're going to have is final minus initial, because that is what a delta always means. A delta is always a final minus an initial there. So we'll take our final of 90 million minus the initial quantity, which is this kind of weird number, but whatever, 393.7500, and that will give us a voltage drop of, a very large quantity. Where's my calculadoro? Let's scroll for it. Oh, come here. And I'm back. What is this here? That's a number I don't want to have to play with. 90, 1, 2, 3, 4, 5, 6, minus 393.7500. Oh boy, we get something giant. That's okay. We're going to get 86062,500 volts. And then, as we started initially in the problem, way back up here, we know that work is Q times that quantity. So our final answer here will be that work is equal to Q, which in this case was 0.5 microcoulombs, so times 10 to the minus 6, times this voltage here, that delta V, of 86062,500. And that gives us a work value of just about 2.5 joules. That's it. Okay? So that is what we want in the end. A work is a charge through a voltage. Even though this is a giant voltage drop here, the charge was very small. So we only got just a teeny bit of work done out of it. Okay? In this problem here, an outside force did indeed do that work. You know an outside force did that work if you wanted to think about it in terms of like what did the work here. Because if we take our two positive charges and we go back to drawing electric field lines, we know that these electric field lines are going to come out and snake up. My first one I drew was kind of bad. It should come out a little farther. They should come out and do this. Which means that if you initially had a point charge in the center, there was no electric field there. If you wanted to move it this way, you had to do work against the electric field. So something had to do that work. Some outside force had to make that happen. Okay? So that's just a kind of little quick thing in addition to that. It was a larger problem than the last one we did, but only because we weren't using the infinity point, as a reference there so that the final voltage, or the initial voltage, was 0. We just had to do that kind of voltage setup twice, but it's very easy to do that because voltages are indeed scalars. So with that, this problem is finished. Y'all take it easy. Have a good one. Adios.